I want to first start with very basic of classical approximation, which is it is called dyadic. So that we have a very simple picture: white background and black foreground with the domain inside this area, right? So the domain is very smooth curve, and what we want to do, we want to approximate this image, this picture, or this bivariate function with dyadic squares. How it works? We start with at this. Let's say we start at this level with these side squares, right? We split the domain into these squares. For each square inside, we look at the approximation error. Now, this guy sits. Let's look at this guy. This guy sits right inside the domain. So the function in this area is 1. The value that we assign to this square is 1. So what is the approximation error between this area, between the function and this approximation? None, 0. The approximation is accurate. Let's look at this area. Let's look at this cube, dyadic square. So as we can see, the border goes right inside. It's white outside and dark inside. So the error is significant, and we decide to subdivide this square into 4 pieces. And then we end up with 2 more guys here and here. Now these guys, they sit inside the domain. We assign to them the value of the background. The approximation error inside this guy is 0. So we decide not to subdivide this square. We decide not to subdivide this square, but we will subdivide this and this squares further on. So as we can see, most of the new squares, very small size squares, will be along this boundary. And this is, on one hand, this is the main approximation algorithm scheme for classical approximation. On the other hand, this is the first red flag that we want that we observe. What is the red flag? If you look at this object, it is composition of 2 super smooth, simple objects. One is the black foreground, white background, and a smooth contour, a smooth boundary, right? And somehow this dyadic approximation suggests to us this so many pieces of approximation. Basically tells us that you will, in order to approximate such a simple object, you will need, let's count how many squares we have. 1, 2, 3, 4, 5, 6, 7. You will have hundreds of small squares. Well, naturally, how we would suggest to do it as human beings, we would first take this contour, we would approximate this curve with a couple of lines, right? And we will draw black inside and white outside. Okay, so let me walk you through how we get into this problem and how AI actually resolves this problem completely. I guess this is the very first approximation theorem or exercise that we all remember from, I guess, Introduction to Approximation on Numerical Analysis 101. It tells us the following. Let's take the function that has nice first derivative, which is either continuous first derivative or a bounded first derivatives in terms of p norm. You can approximate this function with piecewise constant approximation, just bunch of levels, and the error of this approximation will behave in this way. So the smaller steps you take, the shorter steps you take, the smaller will be the error of approximation. So the function needs to be continuous, needs to have bounded first derivative, and then what is h? H is the 1 over the number of the pieces of the steps that you subdivide this function. And it tells the following. If you take your function, run it through wavelet transform, take the first best n coefficients or wavelets from the representation, and this approximation will behave will approximate very nice the original function. And let's look how this approximation will actually do the work. So first we start with the function that is an infinite series of wavelets, and then of all of this infinite series we select m term representation. So there obviously it's not as good as the original function, but the errors the error that we have, the error of approximation, will decrease with the alpha rate. Who is this alpha? This alpha is actually the you can think how many smooth nice derivatives we have for this function. And then we take it further on. So that's the main Jackson theorem for wavelets. Take a function that is has limited into L2 integral and has alpha nice derivative. You can approximate this function. You can approximate this function from n-term wavelet of n-term wavelet sum, and the error of approximation will decrease with the power of alpha. So the smoother the function, the faster will be the approximation rate. So let's see how we can easily solve the dyadic squares problem in 1D. That is something that I have done in my masters. So I looked at B-spline spaces, at B-splines, and I looked at wavelets. So the wavelets, they are defined as complementary orthogonal space to the B-spline space. And you start the story by building a sequence of nested B-spline spaces. So on the left you see the classical wavelet. It's a cubic wavelet, and they will be orthogonal to the B-splines in this space. Now the nodes tell us that for each node interval, the wavelet is essentially just a piece, it's cubic polynomial. So this wavelet is a bunch of cubic polynomials that are connected together at these nodes. So this is the dyadic representation, the dyadic squares in one dimension. How we can solve it? We start to move the nodes, vary the nodes, take them farther or closer to each other, and we obtain different shapes for this wavelets. So what is nice now is that we can actually reproduce much more difficult shapes, one-dimensional shapes. Now, how this representation would look in 2 dimensions? We utilize tensor product. We take this function of x, we multiply it by the same function of y, and it gives us a bivariate function. And as a result, we would obtain dyadic partition of the domain defined by these guys. By solving this problem in 1D, we will obtain a dyadic 2D domain, which is still defined by a line, parallel, and orthogonal lines. What is not the solution that we are after, right? We've seen that in the very beginning that we want to find a subdivision that is able to find the curves, the contours of the discontinuities. So that's what I tried to do in my PhD. And this is the work that was published in this book, and they use. Okay, so I will not go into all these details, but I will tell you. I will just say that there is a link. There is a link between the order of approximation of the order of decay alpha to the functional, the approximating functional that we use that we define when we approximate the function, and to the n-term wavelet approximation. The classical approximation that is defined by this dyadic subdivision operates with the functional that is defined by just these 2 terms. It's a minimization functional, and it tries to minimize the approximation error of the function that you want to approximate with the function that comes from the space that you're using, which is defined by, and it can be an n-term wavelet space. And it is compensated also by the it tries to minimize the derivative of the variability of the function that the approximant. How it tries to minimize or penalize the approximant? It tries to minimize the function's derivative. So the smaller the derivative, the smoother will be the approximant. With this functional, that's what we get. So if you want to be able to introduce nice smooth curves into our approximant, we introduced another term into this functional, which actually takes the edges away from the approximant and brings them into as a penalizing term into the approximant, into the functional equation. And without going into the details, we can see that this new form allows to construct a much more accurate approximant for the function. And these are the real results that we obtain with our approximation scheme versus the JPEG compression. And JPEG compression, JPEG 2000, is based on wavelet approximation. So the original image, we approximated the original image with two methods, and then we maintain exactly the same amount of information in both images, in both methods, and we discarded the same amount of information. So it was very few end-term wavelet approximation. We used very few terms in this place, and we have used very few approximation curves for this image, and this is the result. And I think you agree with me that we definitely, naturally, would prefer to look at this image as an approximation to the real photograph rather than this guy. And I think now we understand where all these artifacts come from. The wavelets, they are very sensitive and they behave very bad when there is a sharp edge. Here's another example, and this is the worst case scenario for any classic approximation. The worst scenario because this is a synthetic image. It's defined by nice, smooth curves. And inside these curves, you can see nice, smooth domains. So it's a combination of smooth one-dimensional and two-dimensional objects. JPEG 2000 wavelets, Fourier, they're not able to find this geometry, and this will be the result, the approximation that you get for this image. If you once you identify these curves yourself and separate them and approximate separately the curves, the one-dimensional objects and the two-dimensional domains, that's what you get, and it is very close to the original image. And as you can see, look at here, you can see that the error that I introduced was actually the geometric error for this curve, because I approximated this edge with a piecewise linear contour. And here's another example. It's a real image, and again, it has lots of structure that should be able to be picked up by the reasonable approximation. Any classical approximation based on wavelets, Fourier, or any other tensor transform would not be. So what is the AI? Let me tell you, and I'm going to show to you how AI solves this problem automatically. Essentially, AI, the very first AI model. How it works? It takes lots of n vectors from the n space. Then it introduces a linear transform from n space vector into one number. So basically we are looking at n weights. Then this number goes through so-called nonlinear activation function that has this shape. And the result will be a number between 0 and 1. Right? So the unknown in this model would be these weights. Now think about if you have many n-dimensional vectors. And for each vector has a label. Think about dogs versus cat. 0, 1. So what we want to minimize, we want to minimize the classification. How these vectors classified at the output. So we want to build minimization function that is able to reproduce 0, 1s exactly as we had in the data. And we want to minimize this function subject to this weight. So the result will be the weights that you find in this minimization. And here's how this simple model solves the problem of the dyadic partitions, dyadic square and cubes. If we use just one, remember, just one activation function, we go from, in this case, what is the problem? We have a bunch of points, hundreds of points, each one has a color, blue versus red, and you want to find the region that separates these two classes of points. Okay? That is how the solution would look with the dyadic squares. You would need to build lots of small cubes along this boundary. Now, if we use just one activator, we will obtain a direct line that splits the two domains very roughly. But when we start to introduce more and more domains, more and more nodes, we can see that we can start to get more and more reasonable shape. Now let's look at the base shape. This shape was successful to separate the two clouds of points, red from the blue. And all we needed to do in order to find this separation, this boundary, it had 4 internal nodes. So the matrix, the linear transform that we used went from 2 to 4. 8 numbers, enough to identify this boundary. And the boundary, as you can see, has a nice smooth curve. If you look at this representation, we would need hundreds of points, hundreds of squares, and our approximation would not be as nice as this one.
Points are the coefficients of the polynomial.
Right, and all we need to find is the linear transform, the coefficients in the linear transform. And then we can decide we can increase more levels. Increase more levels means we can build more complicated model. So this would be one linear transform, and from here to here we would define another linear transform. And if our problem is very complicated, we can define many layers. We would train this model. We would solve minimization problem. Solving minimization problem means running gradient, using gradient descent to find this linear transform from here to here and from here to here. And what is really nice is that there is an explicit formulation for the loss function of the gradient of the loss function subject to all these coefficients, all of them. Right? So the solution with AI is will essentially give us the transforms, the internal linear transforms. Use regularization, or Tikhonov regularization, there are many other ways to call it, and because the original problem is very unstable, they stabilize this problem by introducing regularization subject to the coefficients of the transform, if it's just one layer, or subject to all the coefficients of the linear transforms. Here's another application. This linear transform we can build in such a way that they would represent convolution. Not really convolution, but we can think about a linear product with some unknown basis function. Right? So once you train this model, you have lots of data, labeled data. You want to build a model that is able to identify cats and dogs. As a result of this training process, you will get basis functions or convolution kernels that works the best way for this particular problem. And then there are different configurations. There are many different configurations that you can build with neural networks. And one of them has lots of practical applications. It's called autoencoder or just encoder. How it works, you start with an n-dimensional vector, has many hundreds of dimensions, and you want to see what is the minimal number of dimensions I can use to represent my data nice. So there is a nonlinear substitute for the principal component analysis. You build neural network. The output of this neural network, the internal layer, will have very few nodes, very few components. Let's say 2. This is the inside layer. Then the outside layer will use exactly the same transform or the transpose of for this transform from these two layers into the original number of dimensions. Let's say we go from 100 dimensions to 2 and then back to 100. We minimize the difference between the input and the output of this scheme. So what is the result? The result will be the linear transform from here to here, but we can introduce many of them. So essentially the model will be extremely non-linear. But the solution is that for your million of images, you will find very optimal representation with just very few numbers. And this representation is absolutely non-linear versus the linear principal component analysis. Okay, so how artificial intelligence or deep learning, how they actually get it? Right, let's look at the assumptions of the classical approximation, and let's see how AI actually deal with them. Any multi-resolution analysis starts with a nested set of spaces. We also assume that all the spaces in union, they are able to represent any L2 function, any function. And we also assume that there is a two-scale relation. That means that if this function belongs to this space, then when we squeeze this function, it will belong to the more accurate space. Now AI, we've seen that it doesn't care about this situation at all. If you build AI system for dogs versus cats, it will build set of basis functions for this problem. Tomorrow you want to deal with self-driving cars, you will train the model again, it will build another set of basis functions. Absolutely different. Second, they don't care about this two-scale relation. They work at different levels, but they do not impose this two-scale relation, this dyadic relation, dyadic constraint, onto their training model. Here's I want to explain to you how these principles utilized in a very popular AI system is called convolutional neural network. And for mathematicians, it's really interesting because there is no convolution in this network. They all operate with inner products of basis functions, but these basis functions, they train or they construct in the training process. Mathematicians, they borrow basis functions from Fourier, from wavelets, and so else. They actually build these basis functions for every single problem. So how it works? They have labeled set of images. And for every image, they know what you have in an image. And each image is, let's say, 30 by 30 pixels. So it's about 900 size vector. Then they construct a set of linear transforms. The first stage, they will construct 4, they call it convolutions, but if you look at how they do it, it's actually not a convolution, but it's a linear product with 4 different basis functions. These basis functions, they are yet unknown before you start the optimization. Next stage, they do some other manipulation. They extract the maximum from each 2 by 2 domain. Next stage, they apply linear transform, which is inner product with another 64 basis functions, which are yet unknown, and so forth. So once they define this process and they run this optimization process, the optimization will be able to find this. Actually, it's 32. These 32 basis functions on a very low level, and then on a very high level, then another 64 basis functions in a lower level, and so forth, so forth. There is no two-scale relations between these basis functions and these basis functions. However, you can actually look at them, and you will see that they do resemble to us the shape of wavelets. In terms of the terminology, so again, these convolutions, they are not really convolutions. Mathematicians will immediately identify that we are speaking about inner products with basis functions which are yet unknown. And so now, once we have identified this set of linear operations, we can actually run some image through these operations. We can plug it into the AI system, look at the result, the first result that is obtained by using, in this case, it's six different convolutions, six different inner products, and that will be the result that we obtain at the first stage. Then we can in a similar way, we can look at the next result and the next result, and they are called feature levels. And as I said, if you look at these features, you will be able to identify, to say that very often they look as some wavelet transform or feature extraction transform was applied to the original image. But again, in classical approach, we start with fixed basis set of basis functions, wavelet Fourier and so forth. With them, they will obtain these basis functions for every single problem independently. They will obtain for cats and dogs, for self-driving cars, for in finance, for so forth. It will be absolutely different basis functions, specifically trained for each problem. High-level detail and a low-resolution level. We keep the high-level detail, and the low-resolution level we run through the same process again. Then we obtain the details for the low-resolution level and the next low-resolution level, and so forth. And what is the result? The result is that this signal, this function, can be obtained, essentially is decomposed into a set of details at different levels, 1, 2, 3, 4, and some very lowest low-resolution version of the original function. And recently, a few years ago, they actually utilized the same approach in AI. So how they utilize it? They build the training model. So the number of layers, 1, 2, 3, 4, 5, 6, up to 20, 30. And what each level does, they decide before they start the process. Now, the training process will find all this linear transformation between them, of course. How they replicate multi-resolution? Look at this. So when they get to this level, then they decide to introduce few levels, transform from here to here. Then they separate, they keep this result separately. They hold it, and they don't apply any more transform to this guy. Now, the rest runs through a similar combination, similar set of linear operations. By the way, just the form of itself, I think, reminds us the multi-resolution, classical multi-resolution transform. And then again, they keep aside the result that they obtain at this level, and then they apply some additional transforms of what is left. The minimization problem will try to fit the original data, the original shapes, versus what you get at this level, 1, 2, 3. So the loss function now is defined not by one, but by 3 components. And that is the trick. As you can see, it's different. It's similar, but different from how we would suggest them to work, because in our standpoint, we would suggest them to decompose completely the signal, this function, into 1, 2, 3, 4, 5 components. They do it differently. There is a constraint because they still need to work with a loss function. So the loss function will try to minimize the difference between this level and the input function, this level and this level, independently. So that is my last slide. And what I try to explain today is that AI, deep learning, and mathematics, I think they started by separating from each other, right? AI didn't like these dyadic squares partitions that mathematicians suggested to them. But right now, as you can see, they start to converge. I think they start to utilize more and more ideas from classical mathematics and classical approximation. Thank you, and I guess now I'm open to take your questions.